Welcome to lecture 2 of module 6. In module 6, we have been discussing on condensation and boiling heat transfer. In the last lecture, we have discussed on condensation heat transfer, and we have developed an expression for average heat transfer coefficient for condensation taking place over a vertical surface, vertical flat plate. And in today's lecture, we are going to discuss on condensation heat transfer, for various conditions and geometries. Okay. Now, in the last class we have discussed that for vertical surface H bar, we have found out from theoretical developments that H bar average heat transfer coefficient, the relationship is like this: 0.943, then G is the gravitational force, LV is the latent heat, rho L is the density of the liquid, then rho L minus rho V is the density of the vapor, K L is the thermal conductivity of the liquid whole cube, by we have mu L viscosity of the liquid, then L is the length of the vertical plate, and then on which the condensation takes place, and then T infinity minus T W. T infinity is the saturation temperature of the vapor, saturated vapor temperature, and T W is the wall temperature on the surface the condensation taking place. So, it is of lower, T W is lower than the T infinity, and then whole to the power 1 by 4. So, this is the relationship that already we have discussed. Now, what happens is, this relationship also we know that it is quite appreciable, or it is quite valid in case of vertical tubes also, when the tube diameter is relatively larger in size. Then the question is, if the vertical plate or the vertical tube is in inclined manner. So, if there is an angle of inclination, so this is the vertical direction and this is the plate, and this is the theta is the inclination. So, this is the plate. So, if the plate is inclined, so if the plate is inclined with an angle, or rather making an angle theta with the vertical direction, then the above equation, then the above relation can be used only by replacing G with G cos theta. Okay. So, this is the modifications one has to do for calculating the values of heat transfer coefficient. Now, whatever we have discussed, this Nusselt derivation or the heat transfer coefficient for vertical plate, there had been certain limitations. The limitations for this, for the above derivation, has been, some of the important limitations are, first one we have already discussed, that one dimensional and fully developed flow was assumed. Naturally, this is the flow of the condensate liquid. So, it is the flow of condensate liquid. Okay. Then second part is that linear temperature difference distribution within the liquid. So, linear temperature distribution. This is also assumed. So, that distribution can be different than a linear temperature, it can be a non-linear temperature distribution. And then the third condition is the possibility of having some convection heat transfer through the film also. So, what we have not, so we have not we have not taken into consideration that there is a possibility of having some convective heat transfer through the condensate liquid. What we have discussed is that the condensate liquid is flowing with a linear temperature profile, and this is the heat transfer is by conduction mode through the condensate liquid, but there could be some amount of convection also taking place. So, these are the limitations. So, therefore, that there could be some changes in the or some deviations of the actual values of heat transfer coefficient and what can be predicted from the above relation whatever we have discussed. Now, therefore, these things are being suitably taken care of by Rosenow. So, Rosenow, he has described that nonlinear temperature profile, and he has taken care of two things, and he says that this L V, that latent heat of vaporization, that can be replaced by L V dashed. So, L V dashed will be equal to L V plus 0.68 C P specific heat into T infinity minus T W. So, in the above equation whatever we have got for H bar, if we replace L V by L V dashed, and where L V dash is equal to L V plus 0.68 C P into T infinity minus T W, where C P is the specific heat of the liquid. Under that situation, it takes care of two things. One is nonlinear temperature profile, if there is a nonlinear temperature profile, and second part is that if the film is cooled below the saturation temperature, cooling of the liquid film below the saturation temperature. Sorry. So, Rosenow relationship is the modification of the above equation, Nusselt equation for heat transfer coefficient, and here that L B is replaced by L B dashed, and as I told you that C P is nothing but the specific heat of the liquid, and all properties at T F, all properties, okay, all properties to be evaluated at T F, which is the nothing but the film temperature. Now, with these modifications, that these above equations works fine when for even fluids flowing through or condensation happening in a tubes also over the surface of the tubes also, and then when for fluid Prandtl is greater than 0.5 and C P T by L V is less than or equal to 1.0. So, these conditions, if these conditions are satisfied, then Rosenow equation is successfully applied for vertical plates and cylinders. Okay. Now, so these are the conditions for successfully applying Rosenow modification for vertical plates and cylinders. Okay. Now, there is important thing, whatever we have discussed as of now is the vertical one. Now, if there is a laminar flow, laminar film condensation over horizontal tube. That means, it is happening over the tube, horizontal tube, and on the outer surface of the tube. That means, here it is outer surface of tube. Okay. Under that situation, Nusselt again given a relation it is similar to that whatever is being derived, and in this case H bar average heat transfer coefficient is, here the coefficient is relatively different, 725 0.725, and then we can see it is rho L into rho L minus rho V, this part is known, then G is the gravity, then L V is the latent heat of evaporation, and then K L cube, okay. And then we have D in place of L, now we are putting D. D is the diameter of the tube, and in case of vertical plate it was L, and then mu L, and then T infinity minus T W, and then whole to the power 1 by 4. So, if we just try to look into that, previously it was 0.943 and the coefficient has been changed, then LV is not, because it is the Nusselt one. So, LV is LV only, it is not LV dashed, which is being proposed by Rosenow. So, if somebody wants to use that conditions like say cooling of the liquid film is also there, and also that non-linear temperature profile, then LV dash might be used, and then D is L is replaced by diameter. Okay. Now, when we have say condensation on horizontal tube bank, so condensation on horizontal tube bank. So, under that situation is something like that. So, we have a tube here, there is another tube here. So, this is a bank of tube, and a flow of this is. So, this is the condensate is flowing like this. Okay, this is condensate. So, there are tubes, these are horizontal tubes, we can say, they are placed one over other, and that condensate is, the vapor is here, the vapor is there, the vapor is getting condensed. So, this condensate film is coming down like that, and now this condensate film will be covering like this, and this is the whole thing is the condensate film, it is coming down like that. For n numbers of horizontal tubes, D is replaced by ND in the above equation. So, whatever we have equations in the horizontal tube equation, the D will be replaced by N into D, okay, because number of such tube into the diameter of all the tubes. So, total surface area becoming the number of tubes into the diameter of the tube, that is what is the case. And for, so then the equation, if I write the equation is becoming like this, then H bar is 0.725, and then we have rho L into G into rho L minus rho V, okay, into K L whole cube into L V by N into D, okay, then mu L, here is the change only, then T infinity minus T W, okay, whole to the power 1 by 4. Now, then similarly for an isothermal sphere, for an isothermal sphere H bar is equal to 0.815. So, the coefficient is little changed and other things are remaining, rho L, G more or less the same, minus rho V, into KL cube into LV by, again this is the diameter of the sphere d and mu L, and then T infinity minus T W whole to the power 1 by 4. So, this more or less the same, except the coefficient is getting changed for sphere in place of cylinders. Now, chain has suggested the following relation taking into account the condensation occurring on the subcooled film between two tubes adjacent tubes. So, as we have seen in the previous, when there are two adjacent tubes, there is an expression for H bar we have found out, but what may happen that there could be a subcooled region where some condensation of the vapor may take place, and so some corrective measure has been taken, and then chain has given that information, and according to him that H bar is equal to 0.728, it is marginally changed, 0.725 it was, and now it is 0.728. And then there is a correction term like 1 plus 0.2 into CPL specific heat of the liquid T infinity minus T W, this is the correction part, latent heat of evaporation into n minus 1, n minus 1 is the number of tubes minus 1, n is the total number of tubes. So, this many spaces are there, and we have multiplied by the other things, rho L is more or less the same, G into rho L minus rho V, okay, into K L whole cube into now L V dashed as proposed by Rosenow, divided by, now it is n into d and mu L into T infinity minus T W, okay, and then whole to the power 1 by 4. In this case, n is equal to number of adjacent tubes. So, we can understand this n is the number of adjacent tubes. So, n this part is fine, and this is becoming n minus 1 is because the fluid film which is there, if there are n number of tubes. So, there will be n minus 1 gaps, and then n minus 1 gaps there will be some fluid film on which the condensation may take place. That is what is being given by this, and this is in many times this LV is replaced by LV dashed, and by replacing the LV dashed it gives a sufficiently good result, and it has been found that this relationship gives a good result with the experimental when n minus 1 into CPL into T infinity minus T W by LV is less than 2. Under this situation, it is good match between experimental and the prediction. Okay. Now we will come to a situation which is called a turbulent turbulent film condensation. As we know that as the film condensation take place, then what happens that vapor comes onto the contact of the surface which is cold, and then it condenses and goes down. Now, what is being found that as long as the condensation is very less, the liquid may go down in a very small thickness, and then the flow would be 100% laminar. Then if the Reynolds number if increased, that means if that thickness is increased and all, then what is being found that there could be some kind of ripples and waves are being formed with a higher velocities. The ripples and waves are formed, and that gives different kinds of heat transfer behavior. Okay. So, now what is being so it's very much necessary to find out that when the ripples will come, when the waves on the surface will come, and when the turbulence will be generated. In actually this can be found out. So, Reynolds number, from the help of the Reynolds number, which we know that Reynolds number is an indication of some flow situation. So, Reynolds number here is being defined based on the velocity, and for the based on the velocity means we have to find out the velocity, and velocity means when the fluid is condensed on a vertical surface, and then after that it drains down. Okay, and then under that situation what happens to the velocity if we try to see. So, that we can find out from the relationship that average velocity V x bar, and that is equal to 1 by delta integral 0 to delta then V x into the dy into 1. So, for the vertical plate, okay, V x is the velocity and dy into area is the 1 is the breadth, unit is the breadth. So, breadth is unity. Okay. Now, dy into 1 is that area, and through the area the fluid is coming down with a velocity V x. So, this divided by the delta into that unit area. So, this is the total area. So, this is the volumetric flow rate divided by the area, and it is integrated. So, we get the average velocity, and this is nothing but the velocity expressions we have found out for vertical plates, and if we put that expression over here, then we will get 1 by delta 0 to delta then rho L minus rho V into G into this is the relationship we have taken based on the velocity profile we have assumed. So, for this case it is becoming divided by mu L, and this becoming rho L minus rho V, okay, and then G into delta square by 3 mu L. So, this is becoming the average velocity along x direction of the fluid, and so Reynolds number we know is given as, if we say the Reynolds number of the film, F here F indicates the Reynolds number of the film, liquid film, and that is we know that it is now hydraulic radius or hydraulic diameter into dV rho by mu. So, dH rho Vx bar by mu L and rho L, because we are considering the liquid, and dH is nothing but hydraulic diameter, and we know the hydraulic diameter is 4 into area by perimeter. So, 4 into flow area by weighted perimeter. So, this is 4 into flow area by weighted perimeter. Okay. So, under these situations, if we see here that in this particular case REF, if when B equals to 1, breadth equal to 1, then we can find out REF will be equal to 4 into rho L minus rho V into rho L into G into delta cube by 3 mu L square, and that is equal to 4 m dot by mu L. Okay. And how this is happening? Because here dH hydraulic diameter is basically 4 into delta into B by B. Okay. B is the weighted perimeter breadth. Okay. So, this B we cancel. So, it is becoming 4 into delta. So, if you put the values of dH and Vx bar is known, then we can find out this expression. Or in some cases we may not like to cancel out like this way. We may like to put the Reynolds number in terms of perimeter. So, for example, for say tubes, vertical tubes, for vertical tubes the perimeter P is equal to pi into d, diameter of this. Here that perimeter is breadth, for vertical tube it is pi into d, that is the perimeter. So, anyway, so what we can write many a times it is written as that REF is equal to 4 into m dot by P into mu L. P is the perimeter. Okay. Now, in the present case, P equals to 1 as breadth is equal to unity, that is assumed. Okay. Now, what happens is that what we can find out from this, once we have got that expressions for Reynolds number, and then we can find out that Reynolds number is a function of delta, that we have seen is a function of delta, and delta is a function of x, that is the distance from the top of this over the falling film over the plate. So, delta is a function of x and Reynolds number is function of delta. So, what is happening as we are moving along, say, so in case of condensation over a vertical plate. So, this is the x direction. As we move down, that Reynolds number goes on increasing, and then what is being said here is that when REF is less than equal to 30, the film is laminar with no ripples or waves. Sorry. Now, when 30 less than equal to REF less than equal to 1600, okay, sometimes it is written at 1800. So, in that situation, waves, ripples and waves are found, but the flow is still laminar, and when REF is greater than, say, 1600 or 1800 in some cases, people says. So, it is the different notations are different demarcations are used, but so in these regions 1600 to 1800, rather it is better to say 1600 to 1800 here also, 1600 to 1800, then in that case we will say it to be a turbulent region. Okay. Many a times, so this is what is the Reynolds number situation, and many a times this Reynolds number is also expressed not in terms of mass flow rate, whatever is being discussed, it is expressed in terms of temperature differences. So, Reynolds number sometimes is expressed in terms of temperature difference. So, that we can understand that from the energy balance equations we can find out that Q dot rate of heat transfer, and that is equal to H bar into area into T infinity minus T W, okay, that is the convective heat loss, and that will be equal to m dot into L into V, latent heat of vaporization. From there we can find out an expression for m dot. So, that is why that m dot is replaced, this is equal to H bar then by L V into, say, area and into T H T infinity minus T W. This is the case, and then REF Reynolds number is equal to 4 into, as I show it, four m dot by P into mu L, and that becomes 4 into H bar. Okay. Now, here in this particular for flat plate it is L into B, okay, then T infinity minus T W by, here it is L V latent heat into B into mu L, okay, and this happens to be 4 H bar then L into T infinity minus T W by L V into mu L. Okay. So, this is what many times this Reynolds number is used to find out the case of turbulence, or to find out that what is the value of Reynolds number, because we have understood one thing, that by change of Reynolds number, which is an indicative of the switching over from perfect laminar situation to a situation, though it is laminar, but with the appearances of ripples and waves. When there is an appearances of ripples and waves, there higher heat transfer coefficient is expected, because some kind of turbulence is there, some kind of mixing is there, and then from there it will be further entered into a turbulent flow region. And therefore, McAdams has suggested that when Reynolds number of the film is greater than 30 to 40, then what we expect? When the Reynolds number of the film is greater than 30 to 40, we expect some kind of waves or some kind of ripples that is to be there on the surface and in the film. Okay. And therefore, he expects that some kind of heat transfer coefficient should be high. And how he says? He just says that let the average heat transfer coefficient be increased by a lump sum amount, it is a 20%. So, 20% increase in heat transfer coefficient is recommended. Okay. So, then H bar, okay, and that happens to be 1.13. So, 20% increase. So, H bar for vertical plates 1.13, and the rest of the things remains the same, rho L into rho L minus rho V, okay, and then G into L V to K L whole cube by we have L into mu L into T infinity minus T W whole to the power 1 by 4. Okay. That is what is expected. So, we have seen that how to take care of a flow situation when it is being changed from a linear to laminar to turbulent regions, and when there will be some formation of waves or ripples. So, heat transfer coefficient value has to be changed. Now, there is another terminology that is very frequently used in case of condensation phenomena, that is called condensation number. It is denoted as CO. It is also nothing but also termed as modified Nusselt number, told as Nusselt dash. So, these are basically equivalent, they are equivalent or same. Now, how to say that? Now, if we just try to see that H bar, that is average heat transfer coefficient, okay, for vertical plate, we have seen that it is nothing but a function of a constant, and then we have the relation rho L into rho L minus rho V into K L whole cube into G is nothing but G cos theta. It is the general one. So, it is a theta could be 90 degree, theta could be 0 degree, and theta could be any theta. So, when theta is equal to 0 degree, then it is a vertical plate, and if it is a 90 degree, then it is some other correlations has to be used, okay, for horizontal part, and then LV, and then divided by we have mu L into L into T infinity minus T W whole to the power 1 by 4. So, what is needed is some kind of rearrangement is needed. For doing that, we already have seen that Q dot is nothing but H bar A into T infinity minus T W. So, this T infinity minus T W will be replaced in terms of H bar and M dot, and that is equal to M dot into L V, that into vaporization. So, we can from here we can say that T infinity minus T W is nothing but M dot into L V by H bar into area. So, this is what happens to be, this is the surface area, is nothing but the surface area for heat transfer. So, under that situation, if we put over here, then we can find out that H bar to the power 3 by 4 happens to be C into rho L minus rho V, okay, into G cos theta okay, then KL thermal conductivity Q into A by L, okay, this becoming the geometrical parameters, mu L into m dot. So, doing some rearrangement to this, you will get this expression like this. Now, if you further do some rearrangements, we will get H as C to the power 4 by 3 and then rho L into rho L minus rho V, okay, into G into K L cube by mu square, this is one part, then mu L square, then we will write mu L into P by 4 m dot, okay, this is the another part, and then we have 4 cos of theta and then A by P, okay, by L, this is the another parameter whole to the power 1 by 3. So, now these two terms, if we write now in this way, so H bar into, now if I take this part, this sheet is nothing but mu L square by rho L into rho L minus rho V into G into K L cube whole to the power 1/3, and that is becoming C to the power 4/3 into, this is nothing but Reynolds inverse of Reynolds number. So, REF to the power minus 1/3 into this 4 cos theta, then A by P by L whole to the power 1 by 3. So, this is the rearrangement, and if we see that left hand side is nothing but, it can be written as H bar by K L. So, if I take the root of this, then it comes out to be K L. So, H K L into then mu L square by rho L into rho L minus rho V into G, okay, and this whole to the power 1 by 3. So, this is coming to be H x by K, some characteristic length. So, it is nothing but this thing is basically your Nusselt number, and that is equal to C to the power. So, right hand side is equal to that right hand side. So, we can see in the left hand side, or we can say that this is nothing but Nu dashed or CO condensation number, and that is equal to the right hand side. And in the right hand side, what we find is, right hand side is a combination of a coefficient, that is the constant term, a flow parameter, that is the Reynolds number, and a geometrical parameter, that is your 4 cos theta A by P into L divided by L. This is whole part is nothing but a geometric parameter, this is a flow parameter, and the other one is the constant term. So, we can say that in case of condensation, that there is a terminology called condensation number, which is a function of a coefficient, a Reynolds number, and a geometric parameter. Okay. So, this is the beauty of a condensation number or the modified Nusselt number. So, therefore, there are some, or we can say that in this way, we can say that condensation number is equal to a function of flow characteristics and geometry. Okay. Now, what is being there? There are certain relationship, correlations have been given for finding out this condensation number, correlations. Okay. And we find that for Reynolds number less than or equal to 30, as I said, and for vertical plate where A by P into L equals to 1.0, under that situation we know that condensation number is 1.47 whole to the into REF minus 1/3, and so that is the laminar region. Then CO is equal to REF by 1.08 into REF to the power 1.22 minus 5.2 when 30 less than equal to REF less than equal to 1600. So, it is a region 1600 to 1800, it is a region when there is a laminar, but wavy and wavy flow, formation of ripples, already we have discussed. Okay. And then another one is condensation number is REF by 8750 plus 58 REF to the power 0.75, then minus 253 into PRL, Prandtl of the liquid, to the power minus 0.5. Okay. And here REF is greater than equal to 1600 to 1800. So, this is that means it is the case of turbulent flow. So, these are the relationships are available for condensation number or modified Nusselt number, for which is based on the Reynolds number, and then once we know the values of Reynolds number, we can find out the values of this, and then we can find out the values of heat transfer coefficient. Now, there is the above relationship are also applicable for vertical tubes with when the tube diameter is not too small. Okay. And for horizontal cylinder, okay, no, there is another relation given by Kirkbride for turbulent flow. That CO is equal to condensation number is equal to 0.0077 REF to the power 0.4 for REF greater than 1800. And then for a laminar flow, or for a horizontal cylinder, condensation number is given as 1.514 REF to the power minus 1/3, and for REF less than 1800. Okay. Then, so this is about that whatever we have discussed, the different condensation behavior and everything has been over the surface. Now, it may happen inside. Condensation many times happens inside. So, if the condensation happen inside the horizontal tubes, then the problem is like when there is a horizontal tube, then this kind of situation, this kind of condensation is highly applicable, particularly for condensers in refrigeration, and also in say air conditioning systems. But the problem is that when the condensation takes place inside horizontal tubes, the phenomena is bit complicated. The reason is that inside the tube, the vapor gets condensed and they forms a layer in the inner periphery of the tube, and then they drain out in the bottom of this, and then it flows in the direction towards the end of the tube, towards the exit of the tube. So, it is like this. So, you have say this is the horizontal tube, some droplets will be formed here, they will drain out here, and then they will try to that the bottom layer will try to flow the liquid condensate will try to flow like this towards the exit. Okay. So, that is a kind of we can think of sometimes it is an open channel flow. of the liquid. So, this condensate moving like a through an open channel, because in the upper side in this above this liquid it is so full of only vapors. Okay. Some of the vapors are getting condensed and they are flowing, they are coming down to the bottom due to gravity, and then they are flowing like this. So, this is like a flow open channel flow kind of things. Second point is, when this kind of situation happens in the flow in the condensation in the horizontal inside the tubes, what happens here? When the vapor comes into the cold surface, okay, so then the condensation takes place, but the rate of condensation, if the tube is short, then the rate of condensation is low, and if the thickness of the flowing condensate layer at the bottom is small. So, if the thickness of the flowing condensate layer at the bottom is small, then the rate of condensation is low. Okay. Now, as we understand that this condensation phenomena is a bit complicated and in horizontal tube, so theoretical analysis becomes difficult, but Chato has given a correlation where it says that H bar is equal to 0.555 into rho L minus rho V into G into K L cube into L V dashed, okay, and then mu L into D. This is inner diameter of the tube, because it is happening inside, and then T infinity minus T W whole to the power 1 by 4, and this is when ReV, Reynolds number of the vapor, is less than, and ReV is defined as D diameter, inner diameter into GV. GV is the mass flow rate of the vapor into mu V, vapor viscosity. So, GV is nothing but mass flow rate, that is nothing but rho V into velocity of the vapor, that is nothing but the GV, and that Reynolds number ReV is calculated based on inlet condition of vapor and inside dia of tube. So, one important thing over here is that we can understand, as it is flowing through inside diameter, available diameter for the vapor flow is less, because some of the amount is being covered up by the liquid, but that is being assumed, that is being neglected. Okay. Now, for higher flow rate, Akers, Deans and Crosser has given a relationship that H bar D by K L, Nusselt number, is equal to 0.026 ReM to the power 0.8 into Prandtl of the liquid to the power 1/3, and the error has been found to be very high for this case, and this is for horizontal tube inside horizontal tube. And then we know that ReM is the mixed Reynolds number of the mixture, vapor and the liquid mixture. So, it is actually given as D by mu L into GL plus GV into rho L by rho V to the power half. Okay. And GL is the mass velocity of the liquid and GV is the mass velocity of the vapor, and this is ReV greater than 20,000 and ReL greater than 5000. So, it is applicable for these situations, and REL and REV are, REV you can understand that dGV by mu v, and REL is dGL by mu L, and GB and GL are mass velocities of the liquid and the vapor, and area is nothing but based on area is flow area calculated as pi di square by 4. So, that the portion which is being occupied by the liquid is not taken into considerations under these situations. And one interesting thing I should say, that effect of non-condensable gases so, when we have a condensation of a vapor, and if in the vapor if you have a non-condensable gas mixed with it, then what is happening? There will be additional diffusional resistance okay. That will be there, and also that actual rate of condensation will be lower. Than the case of pure vapor, pure saturated vapor. Okay. So, when there is a non-condensable gas is there in such situations, these are the two important things that also comes into picture. So, then it is a need of simultaneous. So, it is a need of simultaneous analysis of heat and mass transfer. Phenomena. Okay. Now, I will take up a simple problem to discuss on this condensation phenomena. The problem says a vertical tube 50 millimeter diameter and 1 meter long okay, is used for condensing dry steam at atmospheric pressure. Okay. The tube surface temperature is 40 degrees centigrade. Then we have to find out the determine the mass of condensate and B the heat transfer coefficients average determine the mass of condensate, and second part is that compare with horizontal case. So, now for this problem if we have to solve, first of all we have to find out the TF. TF is TW plus T infinity by 2, and this is nothing but 100 degree centigrade is the So, TW is 40 plus 100 by 2, and that is equal to 70 degree centigrade, and at 70 degree centigrade we have to find out the properties. The properties at 70 degree centigrade, of the liquid, say K equals to 0.675 watt per meter per Kelvin, then rho L equals to 971.8 kg per meter cube, then LV latent heat is equal to 2500 kilojoule per kg. See, mind it, so it is kilojoule, so it will be 2.5 into 10 to the power 6 joule per kg, okay. And then mu L is equal to 355 into 10 to the power kg per meter per second. Fine. Now, we have to use, and what we will say that rho V, rho L minus rho V will assume nearly equal to rho L, because viscosity density of the vapor is much lower than the density of the liquid. So, under that situation, when putting in the expression H bar is equal to, by putting this 0.943 into the whole expressions to the power 1 by 4, whatever we have discussed. So, then it is becoming, this value is coming to be 4033 watt per meter square per Kelvin. So, quantity of steam condensed, if we try to find out, it will be m dot is equal to H bar into pi dl, that is the surface area of condensation, into delta T is the driving force, by LV is the, this is the heat transfer divided by latent heat. So, it is becoming 4033 into pi into 0.05 into 1 into 60 divided by 2.5 into 10 to the power 6, and this happens to be into 3600 to convert into per hour. So, it happens to be 54.73 kg per hour. Okay. And for horizontal case, if we try to see, for horizontal case, that means if it is placed horizontal situation, the tube is placed horizontally, then H V bar H L, H vertical by H horizontal, it's the relationship can be 0.943 by, if we put all the things there, 0.725, and then we will have d by L whole to the power 1 by 4, and this happens to be equals to 0.615. Okay. So, H bar equals to then 6558 watt per meter square per Kelvin, and then so condensate also will be m dot horizontal also will be equal to 89 kg per hour. So, that is what we have seen, that in case of horizontal, if it placed in the horizontal with respect to the vertical case, then rate of condensation, rate of heat transfer is, heat transfer coefficient is high, and then rate of condensation will be also relatively more. So, this is all about the condensation phenomena. Next lecture we will be discussing, in this module only, next lecture we will be discussing on the boiling phenomena, boiling heat transfer, and we will take up the theoretical analysis on these, and then we will take up some problem to discuss. In the subsequent couple of lectures, we will discuss on the boiling heat transfer phenomena. Thank you very much.